Testing. So I guess I should start. Just a gentle reminder that in the announcement already, the homework one has been graded. So if you have any question, then you may email TA. The second thing would be the homework 2, which will be due by the end of the Sunday. So I hope you would take the time to finish it. Should not be too difficult. Just make sure that you don't miss the deadline. Otherwise, some marks will be deducted. I think I'll release the solution 2 days of the deadline. Now, after the release of the solution, I mean, we're not accepting your submission, even it's late, even though. The goal today, we will talk about the random variable. Try to finish them. And at the same time, we talk about some Excel and R. Okay, so that's why we're here. Okay. Very quickly, then we go to talk about the little bit about the random variable. I think we just last time we just stopped at the hypergeometric. Okay, but let us review a little bit what we have been doing so far. So we start from talking about this random variable. Okay, what is this? Is just to first to recall random variable is a mapping of the outcome of sample space to a numbers. Okay, and discrete means there's a limited number of them, so you can count them, right? So they count data. Okay, so that's why you can see the all these are counting the number. Okay, they're all very naturally the non-negative number 0, 1, 2, 3. Okay, and the uniform set is the equal likely that each outcome, right? Because the standard thing is like toss a coin or a number the dice. Okay, the same. Okay, Bunoni would be saying that outcome in the sample space can be classified as success or failure, and Bunoni is just saying the number of success, so it's either 0 and 1. Okay, and binomial is just repeating the Bunoni. Okay, independently n times. Okay, so it's just like each trial has success with probably p, and once you've done the first trial, the second trial also has the same behavior, whether it's success or not, also have probably p. Okay, and so on, and asking the number of success. Okay, so do note that the binomial have a simplification in the sense that you really don't care about how you get successful, but just You just want the number of success. Okay, that's simplification. And Poisson is the extension of the binomial in the sense that when the n is very big and p is not big. Okay, and the application of this is, remember, is the n will be, you consider n is the per period of time, and the interval or the time is so small. Okay, and each time success is just very little, and in that case it's Poisson, right? It's a good modeling technique for modeling the arrival rate of certain thing, arrival rate of consumer, arrival rate of error, arrival rate of say flooding, accident. Okay, some relative rare event, then Poisson would be a good idea, right? So the next thing is hypergeometric. We didn't cover a lot, but we just try to finish it now. Is the Poisson is closely related to the binomial. Okay, you remember binomial is in the sense that every trial, okay, is independent. Okay, how you imagine that is, imagine there's a bowl. Okay, it's an urn. Okay, it's an urn. Okay, of balls. Okay, you have black ball and white ball. Okay, maybe black call success, white call not successful. Okay, successful balls and not successful balls. Okay, and the binomial is asking, okay, you pick the ball from the urn. Okay, and the fact that you pick the ball from the urn is the probability, you know, because it's a ratio from number of black and white, right? Suppose you have 3 black and 3 whites. Okay, the probability drawing a black ball would be half, right? The first ball. And consider the case that you put it back every time you draw. Then every time the probability that you draw the black ball will be 1/2 always, right? So basically just imagine binomial is like drawing balls from urn, where the urn have 2 colors, and you're asking with the probability of drawing particular type of ball, how many times you can draw it, okay, and put it back. Now hypergeometric is asking you that, suppose you don't put it back, okay, you didn't put it back. What is probability of drawing, say, 5 balls, okay, out of say 10 balls you have been there, right? Suppose 5 of them are black, 5 of them white. Suppose you draw 3 balls. What is the probability that 2 of the balls are black, for example? Okay, so that is the hypergeometric meaning. Okay, that is the idea behind you do quality control. That's the idea. Okay, so let's see. Did I see the question again? Okay. Consider the case you have a big N number of balls. Okay, there's an urn that has or the boat will have like big N number of balls. Okay, and out of N, A of them are the ball you call good ball. Okay, and N minus A are called the bad balls. Okay, you want to count. Okay, suppose you try to draw small N number of balls. Okay, do some sampling. You're asking if X of them are good, N minus X are bad. Okay, so that is the idea. Okay, just do Y is a quality control, right? Or auditing. How you do that is you go to a warehouse, okay, and suppose the guy said, oh, 99% of them are good. Okay, so in case in the warehouse we have 100 machines are good. Okay, and they said 99 of them are good. Okay, so believe him, then it means that you have 100 machines, 99 of them are good, 1 are bad, right? He said 99% is good. Okay, the question is, you want to test his claim, okay, see whether it's true or not, right? Then you will try to, what you're going to do is you try to draw, say, 10 machines, right? Then you want to see, okay, and you figure out that, okay, 1 machine is broken, okay? They want to calculate what is that probability happening, right? If that probability is very small, then you think that guy is cheating, right? Because it's impossible, right? If that guy, if the probability is like too small for his claim to be true, okay? So we're going to do is calculate the probability of success, right? It's 9, okay? Out of 10 sample you're doing, and you say 100 machines, 99 are good, okay? In that case, you can calculate the probability of this claim and then evaluate whether he's cheating or not, right? If this is so impossible, then you will not believe it, okay? But how to test a claim, or those we talk about this in the topic 5 or 6, topic hypothesis testing. That is what we're saying, but now we're just to calculate probability, just to compare, okay? This n, A over n, okay? If you put the ball back every time, okay? Then this is probability of success, right? Because you draw the first item, the probability of success is A over n, right? Because there's a item that is good, big N of item is bad. You draw the first item randomly, that item is good, is A over n, right? So that's why this guy is P. Is that okay? So this is, remember binomial, which is NP. So same as binomial, the mean. So even though we talk about a sampling without replacement, the mean is same as replacement. So what's changing here is the variance, okay? As we just said, A over n is P, okay? This is 1 minus P, okay? NP times 1 minus P, forgetting the last term, this is the variance as you see in the binomial, right? NP times 1 minus P. And this guy, okay, is actually, we call the, it's less than 1, right? Is what we call the finite sample correction, which means when you have finite number of samples, the variance will be smaller, right? Because you can imagine that you keep drawing the ball from the boat, then you have less and less ball remain, right? And in that case, there's not much variation, right? Suppose you draw all the ball there, then there's no variance at the end, right? So, and do note that if your big N is much bigger than the small n, okay, this term will be very close to 0. Okay, so that means that when you have a very big sample, okay, whether you put it back doesn't matter. Okay, imagine the example I've said that you're going to the warehouse with hundreds of machines, okay? You just draw 10 of them. But imagine the other case, if you go to a warehouse of 10,000 of machines, you draw 10 of them, whether you test it and put it back doesn't really matter, right? So will not change a lot. So that would be the idea, okay? So this is the mean and the variance, okay? And let's go to the, the graph looks really much like the bell shape, okay? But we will talk about how to plot this part in the R later today, okay? If we should have time on that, okay? So here we have the question again. We have 30 computers, okay? 4 of them are defective, okay? What is probably 2 of them are defective out of sample of 6, okay? And here we have, look at the question, there are 30 of them, which is big N is 30, okay? And 4 of them are defective, okay? Here we want to see whether it's defective, so A is 4, okay? N minus A is 26. And you want to draw 2 of them, which is defective out of sample of 6. So the small n is 6, the x is 2, okay? So you need to take some time to digest and see how n and a are related. But just to remind you, the big N is the thing you care to draw, and A is the thing you care, which is, that's why it's 6. And N is the sample you actually draw, the small n, that's why 6. And X will be the thing you're asking how many of them are successful. So this requires you to really work on your problem, you know it, okay? There's not something new, but just apply it. So after the homework too, I mean, you have homework free, then you will be doing. Sorry to make you work, but this is a math. So there's nothing can replace, not sitting there listening is not going to make you work, just like programming, okay? You have to really do the program in order to understand. Okay, so that you'll be doing homework on that one. So we are skipping all the proof there, okay? But before we start, is there any question that you want to ask? I mean, of course, we save some time. We save the time for the programming for the after this section. Okay, let's talk about continuous random variable. Okay. So to talk about continuous random, actually everything is similar to the discrete. Okay. The only difference is the number of value that the continuous random variable can take is continuous. Okay. So that's why the math requires very different, okay? And the idea is similar, okay? But will be different, okay? So, but we'll tell you what's difference, okay? So remember, when we start to define discrete random variable, we start from the bar chart, okay? We start talking about the Px equal to x. So we start from, when we talk about discrete, how we start, okay? Just to recall, we first define this guy, P of x, okay? This is actually the bar chart, right? If you think carefully, right? What is P of x is the standard bar chart. All right, this is x, that's P of x. Okay, that's P of x. Right, so asking you x1 the value, x2 and x3, right? And the height, right? The height of the bar representing the probability, right? So we start from this one, right? And then from this one, the height px, right? Or if you looking the data, right? This is the what we call the I can't draw it. The height of this is called the, if you from data it's called relative frequency, but in terms of random variable probability, right? They're the same, exactly the same graph. And we can draw this f of the graph, right? By combining each bar, right? You combine this to here, this to here, will give you this one. Right? F of x, okay? The cumulative one. So actually for the continuous, okay, it's hard to start from this to here, okay? For mathematics, you have to get from here to here, okay? This is, if you from the data, this is called histogram, right? So we'll get from here to from bottom to up when talk about continuous. So what did I mean by that? So let's see the definition. Okay. So forget about this integration because our class is not about calculus. Okay, but just to have this one first. Okay. This is same as before, right? It just probability f of x is the probability that x is less than the small x. Okay, there's nothing new here. But why we would start from this one first? Okay, the main problem of we cannot start from the px first is because of the idea that when you have continuous random variable, okay, then the random variable actually can take many different numbers that is continuous. It means continuous means infinite many, right? A lot, right? The problem is if every single value, if it has some probability, okay, adding up this infinite number of them, the probability of them will be more than 1 because it must be bounded by 1, okay? Just like if you, for each number, right, you have some value, then you add up infinite of them, then you can exceed, or will always exceed 1, right? But when it's discrete, don't have that problem, right? Because you just add them all thing, it still remain below 1, okay? And indeed, when you have continuous random variable, the probability that each particular value have a probability of 0. Okay, imagine the cases made concrete. Imagine the stock price, okay? And then the stock price can be anything between say 10,000 Hang Seng Index to 40,000, say, okay, for reasonable for the current situation, right? But the Hang Seng Index today may end of particular number will be probably 0, right? The reason why is it may fall slightly more than that, slightly less than that, right? For a particular number, that's very hard, right? Just like suppose I try to throw the ball to the wall, I want to hit a particular point, it's very hard. Okay, hitting near is okay, right? Or just like it's very simple idea. Okay, I have some hair still, luckily. Then I pick up some particular hair over there. Okay, if I just pick up one hair, okay, and I pick that hair that I want to pick, it's very unlikely. You can try it yourself at home. Take up one hair and dye it and try to see if you can pick the one you want. It's very hard. Okay, you can when you pick a group of the hair, you include is very easy. Okay, it's impossible to pick that hair, right? You close the eye, try to pick up some hair from your head, that's fine. Okay, but you try to pick up one particular hair and you just pick up one, that's very difficult. Okay, so that means that we cannot talk about particular number. You can talk about a range of number. Okay, just like you can talk about the Hang Seng Index is between maybe 20,000 to 30,000. There's a range there. Then you can say some probability. That will be meaningful. If you equal to a particular number, it's not possible. Okay, so that's why we will talk about from the beginning of a range is less than the number. Okay. This we can draw a graph. We know what does that mean. It will be same as discrete. Okay, we can think about discrete. Okay, and okay, the next one we want to have something called px. Okay, but we don't have px there, but we instead we call fx. Okay, what is this f of x? F of x is indeed is what we call the histogram. Okay, it's extension of the bar chart, right? So remember the bar chart is the following, right? We call it discrete. We have discrete, right? The bar chart is like this, right? The height is the probability, right? And you can imagine there's actually a bar there, right? Okay, there's probability here. This guy, we actually relate to what we call histogram. Okay. We'll be drawing this, and what we say the area, okay, this area under this F curve will be the probability. Okay, so same as the area below for the whole curve will be 1. Okay, then if you want the area between these 2 points will be probability, same as the histogram or the bar chart. Okay, so the question is how these two are related. This big F, right? This big F is right the same as the one we see before, will be something like this. Okay, at the end we have 1 here. Okay, this F. Okay, how this big F and this small f are related. Okay, and if you learn calculus, right, that will be because the area of this will be the F. Okay, so actually integration. And by fundamental theorem calculus, this is differentiation of that. Okay, but we're not talking about calculus. I just want to, if you don't know calculus, that would be the following. So the idea will be this. For some number here, x, okay? You go here, that is f of x, okay? And what you're asking is how this value related to the value x here, okay? The thing is, if you look at this whole area, the red area will be the number f of x here, okay? The area will be this guy, okay? And similarly, reversely, the slope here, okay, at this point will be the value of this. Okay? So that is the fundamental theorem of calculus. If you learn calculus, but we're not doing calculus, but just tell you how they're related. Okay, so just to remind you again, later you will see, usually we're talking about this value, and you use the primary school math, area between 2 points under this f curve, small f curve, will be the probability. Okay, then I'll repeat this again because we do it again. Okay, although f is something is well defined, but we will always work on the f, small f, or most of the time. And small f, how to calculate probability, right? For this one is easy, right? The height with the probability for the discrete version for the p. But for continuous random variable, you have to calculate the area. Okay, if we're asking what's probability between from one point to the other, then what's probability of this here? We calculate area under this graph. Okay, so that would be the thing. Okay, but let's see the example. Later you will see how we do the calculation. So expectation and the variance, okay? When you have continuous random variable, things become complicated. There will be, actually this guy is expectation, right? And this is actually the probability, okay? But we don't talk about integration here, so that's it's just to give you, if you want to derive the math. But this is no different from the following. You just recall. This is probability. This guy is probability. And this guy is a summing. Okay? Because integration is just summation, summing, but summing up repeatedly. Okay, there's a limit there. But you just this is the probability. Okay, because this is the range of x times this is area, right? If you learn calculus, then you will see this is like this, right? This is delta x, okay, for x. For this value, you draw a bar there, right? And this is the area. Right? So this is the probability when x, and then that's small area is the width of the bar, right? This is the probability for x equal to probability of x, right? So this is the same as the idea of the discrete version. Okay, same as the variance. Okay, I just put it there, not because of you need to remember this formula, but just this is definition. I just cannot say. I just put the black box and say, oh, this is the expectation, but I have to define it. Okay, we are not using this, but just you need to know they come from integration. Okay, that's only thing, the main thing you know. Okay, you need to know the formula, but at least you know this has come from integration, and once integration is something adding something, scalar area. Okay, and we cannot go further than talking about integration because we are you are not supposed to have knowledge on calculus, but just there will be some area thing. Okay, and this definition is no different from the discrete version. Okay, same as this one, the same thing. The distance, the mean from the value from the mean, and then you have the probability here. Okay, so that is the goal. Now, same as the discrete version, I want to show you how to calculate all this. Okay, so but for continuous random variable, it's much easier. Okay, and will be the main core of this 5 different thing. The main thing is normal. Okay, the normal distribution will be using it for the rest of our course. Okay, basically it's just you will see normal and normal again, and also student T. You will see this closely related to normal, and these two will be using for probably the rest of our course. Okay, but let's start with the uniform first because that would be okay. So the uniform is exactly the same in terms of idea, same as when we consider the discrete version. Okay, so when you use this uniform, is you don't know exactly how they're related. Okay, say you may guess a range that usually is like you cannot guess how it looks like, but you can guess a range, right? Just like you look at maybe take the subway or you look at the TV, right? And they ask a financial expert, okay, asking, okay, hey, expert, what is today's stock price? What is the Hang Seng Index today? Okay, and that guy will tell you, oh, the upper bound of Hang Seng Index today is 40,000. The lower bound is 10,000. Always true anyway. But and then you want to see, okay, how you maybe you can make a better expert will give you a smaller range, but they will never tell you what's probability for each thing, right? So what can you learn from that is actually what he's saying is within this range of values, they're equally likely, right? And or if people just give you a range, you don't know what's going on, then it must be how to model that is equally likely. Okay. And again, same as what we said for the discrete version, that is what we call learning, right? Or AI is you assume everything is equally likely, right? And then you keep upgrading by learning from the data or learning from the real world, right? So you and okay. So in this case we have the range between A and B. Okay. So you can imagine, as I said, A can be Hang Seng Index will be 10,000, B will be 40,000. Okay. And okay, so this is a little bit trickier. I will elaborate a little bit more for this too. Okay, what does that mean? Okay, uniform actually means the following. So when you draw the histogram, right, it's actually like this. What I'm doing is the small f. Okay, and I said Hang Seng Index, right? Hang Seng Index that the expert said is 10,000. Okay, to 40,000. Okay, when it's a uniform, it means the following. It means a flat one, right? Because it's every value is equally likely. So the area, no matter you move from, you're measuring from the same width, measuring from here, the same as that here. Okay, and as we said, the area below will be the probability, right? And the expert already said the price will be 10,000 to 40,000. Okay, that means that this area is the whole sample space, right? This is probability. This is 1. Okay, and what does that mean? What is the meaning of what's the height of this? Okay, the height of this will be 1 over 30,000. Why? Just highest elementary school math. The distance between these two is the base. This is a rectangle. The base is 30,000, right? The base times height is equal to 1, right? So this must be 30,000. So that is the reason, right? 4,000 minus 30. That's how we get this formula. Okay, this is the density function. And just to recall this, remind you that this is saying that you give a range, you calculate the area, then you can get from this equation. Okay, just let me illustrate. Okay, suppose now you want to calculate the expert based on the expert claim, it's uniform between 10,000 to 40,000. Okay, so what's the probability that the stock price will be between, say, 20,000 to 25,000? Okay, so let's evaluate this claim quickly. So what is the probability that X is between 20K to 25K? Okay, that basically is that 20K and 25K here, you calculate area, right? That means that is the base is 5K, okay, and the height is 1 over 30K. Okay, K reduced is 1 over 6. Okay, is 1 over 6 probability that the stock price between the Hang Seng Index will be 20K and 25K. Is that okay? So just the area. Now, the most commonly used is this one, the distribution function. Okay, will be forget about this integration. This area, right? Will be the x minus a over b minus a. The reason is very simple. This formula again. This guy 1 over b minus a is f of x, right? Which is the height of the rectangle. And what is x minus a? X minus a is the base, right? Because you're asking a and x, right? And this is the height. The height is 1 over b minus a. The base is x minus a. So we just high school, elementary school algebra, base times the height. Okay, this is the area. Okay, and of course you can do integration, but or you can base from the high school math. Now, these two we don't solve, but this is the math result. But you can easily see why, especially the first one, why it's true. Okay, the value, right, is uniformly between A and B. Your expectation will be A plus B over 2, right? So in this case, right, if that guy said is Hang Seng Index between 10K and 40K, right, the expected value you would imagine is 25K, right? And the variance, okay, this tricky, why is 12? Integration is an integration result, but just to note one thing, I can't explain further, but this only thing we can set is b minus a squared. Okay, b minus a is the range, right? Because this how big and how small is. You give a bigger range, the variance is more, right? And variance is square, so that's why I have a square thing here. Okay, I cannot say further without doing math. But this is the two equations, okay? And probably you are asking, do we need to remember all this equation? And that's no. Okay? If we ever ask you that, if closed book exam will give you the formula, so you don't need to too much worry about this. But is that okay for this one? Okay. So let's quickly go to the other one. Okay. So this is the f of x, okay? If you talk about uniform from 1 to 5, okay? Would be the area below is 1, right? If you talk about just between 2 and 3, this is the whole area is 1. Okay? So this is the f of x, okay? So let's look at this question. Okay. Here I use number of accident. Maybe it's better to change it to a continuous thing. Maybe better is say the amount of rainfall. It's writing. It's very difficult to write. Anyway. Maybe you change it to rainfall, okay? And you can say the rainfall of each day follow a uniform distribution 1 mm to 4 mm. I think it's better because rainfall is continuous. Number is like discrete, okay? So that would be, I think, a better example, okay? And the question is asking expected amount of rainfall each day, okay? Then just apply the formula, right? A is 1, B is 4, A plus B over 2. And this is B minus A squared over 12, okay? So that's a question. So I guess this is nothing important, nothing special there, but I want to ask another question that I think is more interesting. Maybe we have to ask, what is the probability that the rainfall is between, say, 2 to 4, okay? How to calculate that, okay? The answer would be just the following. Just draw a graph here. This is 1 up to 4, okay? And we know the height of this is 1/3, okay? Because then otherwise you don't have the 1, right? This is F. The question is asking, okay, what is between 2 to 4, which is area, okay? And you can use your high elementary school math, right? The base is 2, the height is 1/3, right? So this will be 2/3. Okay. And of course, besides this elementary school, you want to use a formula. You can same as f of 4 minus f of 2. Okay. F of 4 is 1. Right? Because remember how to get f here. F of x is x minus a over b minus a, and a is 1 here, b is 4 over 1, right? X minus 1 over 3. Okay, so f of 4 is 4 minus 1, 3 over 3 is 3. Okay, or f of 4 is like the area below 4, which is 1, and f of 2 is 2 minus 1 over 3. Okay, is 1 over 3 is 2, the same thing. Okay, you can do this calculation or you can do the graph directly. Okay, because this is the formula. Okay, so regardless of the way, you can do the same thing. Okay. Okay, this is the uniform. Is there any question? Now, exponential. Of the exponential, we go to normal. Okay, normal. Then we'll talk about R and Excel. Okay. So let me finish this and then break. Okay. So this one actually is very not difficult. Actually, you have similar idea when you talk about Poisson distribution. Okay. Remember what is Poisson? Poisson is saying that over a period of time, okay, you're asking how many people is coming. Okay. So I think that would be a useful diagram. Okay. What we're doing, the Poisson is asking the following, right? So this time 0 to time t, okay? You are a store owner. You can imagine that over this time, maybe there's actually some people are are coming, right? And then Poisson is trying to model how many people are arriving. In this case, we have 3 people coming during the business period. Okay, so you can use Poisson to model this as how many of them. Okay, so the next question, highly related to this one. Okay, number of customer arriving is a discrete. We're asking another question that's a continuous random variable. We're asking what is the time, okay, needed for the first guy to arrive. The timing, okay, and this time is a continuous random variable, okay, and because of the fact that each arrival is independent, it's also the same as the second guy, the third guy, and then you don't have the fourth guy because you don't have the last one coming. Okay, so the time from not knowing to entry and all this would follow the exponential distribution. Okay, and you ask what is exponential distribution, why exponential is there, and under this, okay, what's the time for arrival? We look like this. Exponential in that sense is let me draw it out. You will see. Why not drawing? Why? This f looks like this. Okay. It means that there will be very likely that they come sooner than later. Okay, exponential. Okay, that is what the Poisson, they will come, they should be able to come earlier than later. Okay, and is there a question before we go to detail, more detail? So exponential is just like, look at this, the above is the Poisson arrival number of customer, and we talk about the time for customer to arrive. Okay, and you may ask what is the application for this, right? The application you imagine is like you are a Chinese restaurant, right? In Chinese restaurant, you're making some dim sum, right? Or you prepare some drinks, right? You have to be hot, or then you have to calculate time before the first customer arrive. You have to make sure that the food is at least half ready, even not fully ready, right? And this is why you need that. Or why exponential is needed. There's a lot of cases that you have to model the timing. Okay, that would be following this kind of technique. Okay, and I want to emphasize a little bit of this. This Poisson is not the only way you can model the timing. Okay, but this is the easiest way you can model, same as Poisson. Okay, Poisson is not the only way you can model arrival, but the easiest thing you can do. Okay, why Poisson is easiest? Poisson is easiest no matter you cut any period of time, right? The number of rays that arrive is the same. Okay, it means that I ask you to cut this timing to half. Okay, Poisson actually means that the probability would be just half of that, right? So if you are expecting, suppose you're expecting 4 people to come in the whole period, if you cut it by half, this first half will have expected value of 2, right? If you cut it into four pieces, it will be 1 in each pieces. Okay, so independent of how you cut it. Same here, the same independency would occur here, right? It's like the special case is what we call the memoryless property. Okay, so that is important property. We don't want to go too technical, but what it meant is if you're waiting, just like say the emergency room, okay, you're waiting at the hospital. If the waiting time follow a exponential, okay, it means the following. Okay, what is the probability that for the next hour, you will be seen by a doctor? Okay, this probability. Next hour, seen by a doctor. Okay, will be independent of how much time you have wait there. Okay, if you wait 1 hour, okay, you only wait 1 hour. What's the probability that next hour you will see a doctor? Okay, it will be the same regardless of how much hour you have been wait. Okay, so that would be what we call the memoryless property. Okay, you tell me that how much time you wait actually have no, have telling nothing. That is what we call memoryless, but of course, that means that this is very convenient. Okay, but of course, is it realistic? Probably not for some cases. Okay, but say for flooding, okay, for talking about catastrophe, I think it's fine, right? The probability of getting flooded for certain area is independent of whether you get a flooding in the past or how many times have no flooding, right? The probability of next year get flooded, same, right? Regardless of how much time we have been there. But anyway, I should go back to the slide here. So as I have hinted, this is exponential. Looks like this dropping. If you plot this, right? This is a decreasing in x, right? When x is small, this is the largest as 1, right? When this is infinity, this guy is 0. So just like exponentially dropping. And you don't have to remember the formula, but you have to remember the shape. Look like this. Okay. And the distribution function will be 1 minus e to the negative number x. Okay. And I think the most important thing to don't even remember, but you have to notice is the expected value of x is lambda, 1 over lambda, and variance is lambda square. Okay. So this is slightly different from the Poisson. For Poisson, the mean and the variance are the same. But here, the mean is and the variance are related by square. Okay, it's very interesting thing. Okay. Before I end, I want to give an example. Okay. So this graph, I don't think is important, but you do notice that the smaller the lambda, the flatter this thing. Okay. Remember the lambda is what? Lambda is in fact, you take x is 0, the height of this, the height of the f at 0. Okay. So that's why when you look at the graph, right? When it is 0, this is 0.5 here, and this is 0.2. Okay. So the higher the lambda, they're going faster, slow, quicker, right? Because the area must be 1. The whole area, no matter you look at the blue line and the red line, they must be 1 below. So if higher this is drop faster, right? The higher the lambda, the faster you need, right? So that's why the mean is inversely with the lambda. Okay, let me repeat the argument, right? Why your mean is inversely with the lambda? Okay, because look at this equation. Okay, look at x equal to 0. X equal to 0. This is 1. This is lambda. Okay, that means the y-intercept is lambda. Okay, and we know they're dropping, right? Blue one has higher lambda, right? 0.5. So it's start from here. This drop, okay, and it drop faster, right? This drops slower, okay, because the whole area must be 1, so it cannot be drop faster. If it drop faster, this area will be smaller. The red will be smaller than the blue, so it must be slowly, okay. And this thing, right? It drop faster, and that means that actually the mean will be smaller, right? Because you have the area of this blue one will be concentrated here compared to here. So the higher the lambda, the smaller the mean. So turn out to be, interestingly, it's just 1 over it. Okay. And the variance will be somewhat related to the idea, right? Because all the value, when bigger the lambda, all the value will condense it near zero, right? Because you can see all the values are much more likely contained as zero. So the variance will be smaller, okay? But I'm not going to prove it, okay? Just before we end, I'll give an example of this and then we have a break, okay? So here is, we have the example of the following. We have the time for first customer to arrive, okay? As I said, why we care about this is you may be caring about your coffee shop. You have to prepare a cake and coffee, right? You heat up the coffee and you cannot just wait until the customer arrives, okay? So you have to start heating up stuff, okay? And we assume this is Finite Poisson, sorry, exponential, right? Time will be exponential, number will be Poisson. So the question is, what's probably that another customer arrive in next 10 minutes, okay? And first is we look that x is 20 means lambda is 1/20, right? Because remember, expect x is 1/lambda. When you say this is 20, okay? Sorry for the poor handwriting, but this is very difficult to write. Okay, that means that lambda is 1/20. Okay, so that's how you get this equation. And once of this, asking next 10 minutes, then just asking this, right? What is the value of x is from 0, 1 up to 9 and up to 10. Okay, so this f of this exactly f of 10. Okay, and it will be 1 minus, just apply the formula. Okay, so before I break, you may ask the question is, what is the probability that x is between, say, 5 minutes to 15 minutes? Okay, so I will have a break here, and after the break we'll talk about this answer. Okay, let's have a break. Maybe we keep it short, 10-minute break, 10-minute break. After that, we'll talk about normal, then we'll, at the same time, we're working on Excel and R, okay? Because that, we cannot do it by hand, so we will be working on the computer. Okay, just resume. So just to talk about the Poisson again, because I guess some of you asked me the question during the break is why Poisson or why exponential? But that is the simplest way you can model how things arrive. Okay, just the Poisson actually just means the arrival of customer. Okay, is only depends on how long it is. Right? The same is uniform over the time zone, and exponential just saying that no matter how much you have been waiting, okay, the time that the people would come is the same. Okay, the next minute, how likely he will come is same, no matter what. Okay, so in this case, asking the probability that there's a customer arrive in between 5 minutes and 15 minutes. Okay, how do you calculate that? Okay, but that will be just when you draw a graph, right? You have 5 and 15. You have this curve, right? Asking this area. Okay, and since we don't know calculus, okay, so rely on the following, right? Is just F15 minus F of 5. Okay, why? F of 5 is this guy. F15 will be just this guy. Okay, so high school math, red minus purple give you blue. Okay, just to repeat, you want to have area between 5 to 15, right? Under this curve, which is this blue area. But we don't know how to do integration, but we're shortcut. Okay, we know everything to the left. Okay, everything to the left of 5 is the purple one. Everything to the left of 15 is the red one. Okay, so we know the answer. And everything the red one will be 1 minus E negative 1 over 12, 15. Okay, and the same idea here, 1 minus E negative 1 over 20, and then 5. Okay, so and then use your calculator, you can calculate this, right? So there's nothing very deep here. Is that okay? Sorry for the handwriting, because that screen is very, very difficult to write. But I hope it's okay. Is that okay? Is that okay? So now we are going to, don't worry, this kind of style question we'll do immediately for the bell curve. Okay, so don't worry. If you don't follow, it doesn't matter, because we'll do the same again, all for the semester. You will say the rest of the class is rest of the course is very boring, but yeah, but this is the same thing. With this normal thing, we will see it again. You will know it. Okay. So, what is this normal distribution? Okay, and probably we have hinted. This is the bell curve, and bell curve is. You may ask application. I mean, the application is. First thing is you'll be using this for the rest of our course. So this first application, you're doing this basically for everything there. Okay. The second thing is the bell thing or the normal thing is like it's so commonly seen it in everywhere. Say IQ in the population follow a normal distribution, a bell curve. Look at the weight and the height is also a normal distribution. Okay. And most of the thing you see in this world, if this is come from the random nature, is a normal distribution. Okay. Okay. I emphasize normal. That means that look at the income. That is not a nature stuff. That's not normal. Okay. We actually know income is a right skewed one. It's not a bell curve. Bell curve is symmetric, right? The bell curve. Okay. Maybe let's look at the bell curve first, right? Because you would be what I mean. The bell curve is like this style bell curve. Okay, it's the bell curve style, right? This is something we usually often seen it. Okay, and you may ask who make this bell curve? Look at history. the bell curve is invented by a genius mathematician called Gauss, okay? And he used it to talk about the measurement error in physics, okay? Measurement error means that you try to use the machine to measure stuff, okay? And the machine is not perfect accurate, okay? And then that will end up with this, okay? You can imagine that the standard thing, if I think you learned in high school probably, is use a ruler to measure the length of object, okay? And no matter how careful you are, if your ruler is accurate enough, then you always have human mistake, then you cannot always make the same thing, okay? And when you plot the error, will be something like the green one, okay? You will be, most of the time, you may be lucky, you get the same, you get the right thing, but you may be getting more or less here or there, okay? It's very difficult to get too much different from that, but mostly concentrate at the center, okay? And same as IQ, right? IQ, I think 100 IQ is the mean, okay, in the whole general public, okay? So, of course, if you look at the IQ in this class, of course, it's way much higher than 100, right? Because you pass the DSE, you come to CHK, you come to B school, we're likely that you are much smarter in terms of IQ than others, right? So you no longer this, right? But anyway, the second thing I want to talk is the support of this normal, okay? That is different from what we learned before, right? Poisson is from 0 to infinity, okay? This one is even you allow negative infinity, right? Because the measurement error can be very big, right? And so that's why we have this. But do note that even though I have infinity here, in most of the cases, like there's nothing, they usually the infinity will not into our concern, right? Because later you will see there's nothing, almost nothing beyond 4 standard deviation from the mean, okay? So even though we allow to be infinity and infinity on both sides, the bell curve would mean that most of them is concentrated at the center. So that's why you don't actually worry too much about things that is too far away. But in theory, allow it to happen, okay? So this is one thing we will do. The second thing here, you can see we have somewhat, I don't know what's going on here. Looks very crazy, okay? Since you see something crazy, you immediately notice that actually we don't need to remember, right? Because we are this non-technical class, so we're not going to remember all this, okay? You can see a square root, you have pi, you have e, okay? What can be more real than this guy, okay? But what I want you to know is because of this guy, you can generate a bell curve, okay? And of course, why this is curve makes sense. Of course, that's a math, we can prove it, but we're not going to prove anything on that. But what I want you to point you to is there are two things, mu and sigma square, okay? And these two will be turned out to be the mean and the variance, okay? So there are two things that can give you this normal distance. This two we call parameter, okay? There's the two things, and you will see the mean appear here, okay? There must be something, okay? And you have square, okay? So if x is greater than mu or less than mu, it's symmetric on the mu, okay? So that's what the bell is symmetric, okay? That's the only thing the first thing I want to know. The second one is the sigma, okay? The sigma appear here, okay? Later you will see that this minus the mu over sigma is a very important thing. Later you will see very soon. But just what you need to know is you get yourself comfortable with this something look ugly or monster, okay? Don't need to remember, but just in your mind, there's a monster there, look like this, okay? Just look familiar. And then this monster have the mean mu and sigma squared, look like a bell, okay? And because this is the mean and sigma. So there's interesting thing is look at the next picture. I hope that would be give you some idea about this monster, what it means. Okay, again, we have to deal with this monster, even though it look ugly, but it's so commonly observed. We'll probably try to prove why this monster is so common in the next topic. We call the central limit theorem, which essentially said when what the variable you observe is coming from many small random stuff, okay, then you observe normal distribution. Okay, that's why the IQ, the weight, the height. Okay, your IQs depend on your genes, your mom's, which basically your mom and dad's genes, and also how they randomly combine together. If you learn biology, right, and that is very random, and also depends on how your brain develop and what kind of food you eat, right? What kind of friend you have, you get your IQ. Same with the weight and the height, right? What kind of food you eat, how much exercise you have done, and then so many things are more or less random. Okay. But anyway, what I want to say is here you compare the red and the green. Okay, red and the green have the same mean, mu. Okay, and the sigma. Okay, the green one is smaller than the red one, right? So you will see that when the sigma is smaller, then you squeeze everything in the middle, right? Because area must be 1, so that has higher peak. Okay, so look, compare the same mean. The larger the sigma, the flatter, right? You bigger sigma, you just smash it and then you spread out. Okay, smaller the sigma, you're more concentrated in the center. So the first thing observe, and the next, that's why in statistics, sigma is called the spread parameter. Okay, the larger the spread out more. The next one is mu. You compare. Okay, I cannot never go that one. Okay, the next two graphs is the blue one and the green one. Okay, and the difference is they have the same spread parameter but different mu, and you can see they're identical except they move a little bit. Okay, that's why in statistics the mu is called shift parameter. So just basically shift the distribution. Okay, so the repeat normal is very simple, right? Just change the mu, we just move left or right. And sigma, you just like smash it how hard, right? The higher the sigma, you smash it and you press it. Okay, you press the bell. That's the only thing. Okay, is that okay? And now we're going to do some calculator, because as you can see, this object, I mean, even though you take M2, those who do the M2 will notice this integration is hopeless. You can't integrate it. Okay, if you can, you get Nobel Prize. Okay, you get the $1 million. I mean, more than 1 million, because you cannot integrate this one. Okay, we have to use either the table or calculator or Excel or R. Okay, there's no way you can do it by hand. Even though you want to do it by hand, there's no way. Okay, so we have to rely on computer. So that's why you're here today, because we need to use computer. Okay, the first thing to ask is normal distribution have different mu and sigma, right? Based on the sigma and mu, that look different, right? Because you use different mu, you move around. Your sigma, you smash the thing, right? Then the question is, do we need to create a table or create a function for different mu and sigma? Okay, the answer is no, because there's a very interesting thing. It's called transformation, or we call, in technical term, we call standardization. Okay, we use all this thing many times in the semester, so don't worry. What you're doing is, if you take your variable, subtract the mean, which is mu, over the SD. Okay, if X is normal, if you do that, always you will get a normal with mean 0 and 1. Okay, So this is not surprising. Look at the graph is you subtract the mu, basically you sieve everything, you subtract every data, okay? By mu, just like you sieve everything back to 0, right? Look at this diagram. Before, right? If you add every value, just sieve, right? And then you divide it by sigma, okay? Okay. Here basically is here you just multiply, just solve it up, okay? So that's why you divide it by the sigma, you get back this guy, okay? Why you can prove it, but it's not our goal to prove it, but just telling you this is true, okay? You subtract, give you a random variable, subtract is mean, mu is normal. Over this is called standardized normal, okay? And why is it true? We're not going to prove it, okay? But what it means is we do not need to create table for every mu and sigma. We just need to create what we call the standardized normal with mean 0, sigma 1, okay? Our life is much easier. That's why you can look at table, okay? If you are given a table, you can just look at the table, then you are done, okay? So the second thing is like the table can be even simplified by the fact that the Bell is symmetry, okay? So that's why I look at the table in the book, most of the book. They will only give you a negative one, okay? And remember this word, this is f of z, right? It's less than. So why is the case? There's a bell curve there, okay? And why only give this area, okay? This is the z, right? This is what we call the z table. Only give the area from negative infinity to 0, okay? You don't need to worry about this number, okay? Suppose this is a. You don't need to worry about this number, okay? Maybe just to be more concrete, right? Say, the table only gives you -3, okay? You don't need to calculate, you don't need to worry about 3 here. The reason is that because the bell is symmetry, the red yellow area same as the red area, right? And if you want, what we want is calculate blue area, right? Okay, but you know blue plus red must be 1, okay? So blue will be 1 minus red. So you find the yellow, 1 minus yellow is blue because yellow is red, okay? Of course, with Excel, we don't need to worry about that, but you still need to know this thing. I mean, of course, in case you go to other classes, right? Or you don't use the table, then you will be doing that, okay? So that's what I said, okay? Because symmetry, this is same as this guy, okay? The graph is here, okay? Let me repeat the agreement because bell is symmetry, okay? Yellow is equal to red, okay? So you want to find the blue, will be 1 minus red, okay? The same idea here, okay? Now, if you know question, then we actually do, when you see C table, we will not look at C table because we're here, we'll look at the Excel, okay? And then we'll try to look at Excel now, okay? So the first question is asking, suppose I have a standard normal, which is normal with mean 0, sigma 1, okay, or sigma square 1, okay? So I want to calculate this, okay? Just to remind you again, this means normal 0, 1, okay? Mu is 0, sigma or sigma square is 1, doesn't really matter, okay? So we want to find this, z is less than 1.4, okay? So just to remind you what it means is you have a this, okay? 0 is here, 1.4 is here. You want this area. Okay, so that is the goal, what you're doing. Now, what you're going to do is go to the Excel. Okay. So the function we're using is called norm S, is normal, standardized normal. And this, okay, is distribution, okay. And we have what we call 1.4, okay. This one, okay. So there's a remaining argument here. We see cumulative or not, okay. So basically for all of our purpose, okay, always true, okay. And you want to ask what's true, let me explain a little bit quickly, okay. So what is true and false, okay. The true actually means when you put true, we have true here. This is f of x. When you put false, this is fx. Okay. And I don't think in any case you will need to calculate fx. Okay. Just to remind you what's fx and big F and small f. When you say true, Excel gives you this one. When you have false, Excel gives you this one, right? But you almost never use this for our class, basically this one. Okay, so we have this number 0.9 is coming from here. Okay, is that okay? So now I want to let you see this two guys, okay, less than 1.6, okay. How do you calculate that one? Just to remind you how to do this guy, okay. Is this, right? A bell shape, 0 here. This is the area, right? So how do you calculate that one? Okay, that is rather simple, right? Just go to the Excel, type norm as this, right? Negative 1.6 and take true. Okay, so let's do it. Negative 1.6. Okay, so basically again we have norm standard this negative 1.6 true. Oh, I think I make some mistake here. Yeah, this I forgot the S. Okay. So the area is rather small. It's only 5%. Slightly rather than 5%. I hope you can get the answer as I got, because we'll be doing this a lot. Is that okay? Hope that's okay. And the next one, what we'll be doing is this guy, okay? This one is asking negative 1.6 and 1.4, okay? So let's see. Negative 1.6 and 1.4, okay? And this is 0 here, asking this area, okay? So again, how we do the calculation is you calculate the red area first, right? And you subtract from the purple one, okay? The red one, actually you have calculated at the beginning, which is this guy, okay? And the purple one, we just calculate, it's like 5%, okay? So the blue is red minus purple. Is that okay? So you can just ask the IQ, right? What's probability between normalized after 1.4 and 1.6? Okay, so that is, as you said, very commonly used, commonly question asked. Okay. So if there's no problem, then let me talk about another thing as well. Is completely reverse what we have doing. Okay. Here I have to give you a number. I want to do area. Now reverse. I want to ask the area, give number. Okay. So what does that mean? Okay. Then we have a whiteboard here. So far, what we have is normal, okay? And okay, I give you the Z, okay? The Z, you give me the probability, right? That is, the formula for this will be norm in Excel, right? This, okay? So what happens if I want the other way around? I give you the probability here, okay? What is this guy? Okay, this we call norm S inverse. Okay, norm S inverse. Okay, so let's see is that okay? Just reverse what we're doing. Okay, before I give you number, give me the area. Now I give area, you give me number. Is that okay? So let's see the example. Hopefully that I can convince you. Okay. Now we found the Z such that Z less than Z is between 0 and for any given number. Okay. And do note that our notation here is we call the Z alpha is the one on the right tail. Okay, not the left tail. Later you will see why we define. Next chapter you understand why we define this way. Okay, but let's consider this one. Okay, later you will see these two numbers very often, but here what is said is what is the probability that Z on the left hand side is 9.95. Okay, so the question asking what's this guy is if we have this normal, okay, and if this area is 0.95, I hate it. 0.95, okay, what is this Z? What is this value? Okay, and we just said how to do it. We'll be doing is a norm S inward. Okay, so let's do it. We'll be doing here norm dot S dot inverse 0.95. Okay, so let me copy this guy again. So this is 1.94485. So this magic number you will remember because you will be doing this. This will become part of your mind. Okay, so don't worry, this number, this magic number, you remember as much as your boyfriend or girlfriend birthday. Okay, if you forget, you have trouble. Same as this. If you don't know this number, you have trouble. Okay, you have trouble with this class. Okay, you should remember this one. Okay, because it appeared many times. You can't forget. Okay. So is that okay? Just this guy. Okay. So the next question is the other way around. Asking bigger than this is 0.25. Okay. There's a 0 here, and we have asking this area is 0.025. What's this guy? Okay. And we know that the area below must be 1. So use the complement rule, actually, right? The red one will be 0.975. Okay, that's what it means. Okay. And we just do norm dot s dot inward 0.975. You get it. Okay. So you give you 1.96. Again, these two numbers, it's just like your boyfriend or girlfriend birthday. Okay. If you forget, you have problem. Okay. Let me do it. What you want is norm s dot inward 0.975. Okay. Okay. Just the number. Keep in your mind. This will be the thing you need. Okay. This is the two number that you always have. Is that okay? These two numbers so important. I remind you again, you'll be saying this all over the course. Okay, so don't forget it. Now, before we end, we go back to the original question because standard normal is just a special case. Okay. You want to calculate this, right? Indeed, right? This, suppose the thing you want to study has normal with mean 20 and SD is the sigma is 16, right? Just remember this implies sigma is 4. Okay. But the question is, what is the probability less than 16? Okay. So one way out is to follow the idea this less than 16, okay, is coming from, you can do this is the thing, this is inside, you can do the following, x minus 20 less than 16 minus 20, right? The same thing. You subtract both sides from 20, this is exactly the same, okay? Then you divide both sides by 4, it's the same, right? And this guy is standard normal, okay? It's less than 1, okay? And this one you can use what we have just learned to calculate this number, okay? Of course, we are smart, we don't have to do this, we can do it once and for all because we have a formula called norm this, okay? And you put in the number 16, put in the mean 20, and I think you put SD4, and then you put true, then you're done, okay? So let's do it. So this is 2016, okay, 4. Okay. Why it's not coming out? Okay, so let's go to the screen, Excel here. You do the norm dist, okay? And then you have the mean is, I don't know, 16, right? The mean is 20, standard deviation is 4, and true, always true, remember for our class. Okay, so this is how you get the answer immediately. Okay, norm this is the mean, this is the SD. Okay, so quickly, you know how to calculate this, grade 24. Right? Let me finish this question and then we end because I don't want to someone who will need to take the bus. Okay. So basically it's here we have 20 and we have 24. We're going to ask this, the red one, but we're the same as 1 minus the blue one, right? The blue one is calculated by this probability, sorry, norm this 20, sorry, it's 24, right? And mean is 20, and the variance is, the SD is 4 and true, okay? 24, 20, 4 true. So you will be like this. So how to calculate that one will be 1 minus the norm this, okay? And we have 24, mean is 24 and true. Okay. Actually, it's good to see here, right? The red is here. Okay. We want 24 below. This is blue part. This part is blue. 1 minus the blue is the red. Okay. That's it. I don't want to keep you too long because already many of you may have to run. Okay. So yeah, that's it. So just remind you, homework 2 is due this Sunday, and homework 1 has been released. You can look at the blackboard. If your question, just ask TA, not me, because I'm not the one graded. So any question, ask him. If you cannot resolve with him, you can go to me, but we'll do that first. Okay. So I hope we end today. We almost end this topic. So next time we will continue this thing. I guess if possible, you try to bring your laptop because we don't have time to finish all this. But if good, can you next week you bring your laptop because we want to talk about R and Excel. You don't have to bring it because it'll be very simple. But if you really want to work it out, you are encouraged to bring it. Okay. So I see you on Monday. Have a nice weekend. Enjoy.